Okay, so this equation should be sufficient, but let's just change a little bit the units. Generally, what are the units that we know for omega? Would be radians per second. But most of the time, if not all the time, your car, you don't have the velocities of the engines radians per second, you have them into revolutions per minute, no? RPM. So let's just rewrite the same expression in function of the RPMs. So let's say if we know omega, so we have radians per second. Okay, so it should be equal to what? Radians per second. So I need to transform that into RPM. So we know 1 revolution will be around the full circle, so 2 pi radians. And then we know there is 60 seconds in 1 minute. So let's see, this will give us what? So you see all these units will cancel out of radians, second, and we are left with revolutions per minute. So the transformation between radians per second to revolutions per minute will be 60 divided over 2 pi omega. So it will be revolutions per minute. Or actually, you could write this as what? As 30 divided by pi revolutions per minute. Okay, so it will be your omega. All right, so we can say substituting into the expression for WT. What do we get? Two pi over times D, or this will be equal to, so it's not 2 pi here, it's 2p. I don't know what I'm doing, 2p. So it will be equal to 2p divided by n times d. And now I will define what is n. Well, n will be just equal to 30 over pi omega. So this is the RPM, the revolutions per minute, at which your shaft will be turning, okay, or oscillating. Okay, and the name, so N is known as the rotational speed. Okay, so again, what is one of the definitions now of power is what? It's force times distance. So this is work, force times distance divided by time is power, no? Okay, so you could say that power is kind of also equivalent to what? V times distance over time, which is what? Velocity. Okay, so following this equation, it can be we can say that the power generated by the force omega sub t would be equal to omega sub t times the velocity of that force. Or from this one, this will give us that the tangential force will be equal to the power divided by v sub t. And v sub t is what is known as the pitch velocity. So basically, again, I mean, I'm showing you all this stuff, but don't think we're gonna go really into details. But depending on the gears, the teeth you have, you will have some recommended pitch velocities or a maximum pitch velocity that you can have in order not to break that gear, no? Okay, so sometimes you will have that available. So if you know that available, you know the power you need to transfer, or let's say you know the power you need to transfer, you know the pitch velocity, you can find out what is the value of the force, no? That will be on the side, apply on the gear. So the force that the gear will be applying to the shaft. All right. Okay, now something you need to be careful. So it's direction of forces on mating spur gears, or just gears if you want. Okay, so I'm going to write over here representing the forces. I'm going to put moments acting in their correct directions or direction is essential, obviously, to an accurate analysis. Okay, and that is generally the most difficult part in structural engineering. It's not that much to calculate the stresses, and everything else is to find the correct loading for that structure. Okay, so here what I'm trying to say is that, let's say you have a shaft over here. You might have one shaft over here Let's say that one has a gear, but now let's say this one will be connected to another gear over here. Let's say it can be smaller. And this one can be connected to another shaft, no? All right. So obviously the force applied on this one over this gear will be equal in magnitude, but should be opposite to the one acting on this one, no? From the principle of action-reaction. Okay, so that's basically what we're gonna be saying. So let's say if we look at here at this location, let's say you have here the gear over here, and then another one here. So let's say this will be A and B. So we have here the radial force. This will be here the tangential force. So let me be specific here. Let's say this is on gear B, the force acting on gear B on gear B. So if I do the same figure, okay, so using principle of action reaction, so remember, this is moving in that direction, this will be moving in that direction, this is moving in that direction, this will go in that direction. So now what will be the forces? If we look at the other direction, this will be WR on gear B, on gear A. And this will be WT on gear A. Okay, so depending on which shaft you're going to be studying, you will have to use different directional forces, no? And I also put moments because what's going to happen? The forces will be acting at a certain distance from the shaft. So this will also be producing a moment, no? Yeah? Okay, so a moment can be, you know, positive or negative. So this is an important part. Okay. Okay, next, again, I'm going to put it, but I don't think, wait, I'm not going to give you problems that would be that, because that would be really design problems, and I don't think they have much to the understanding. So let's say interference between mating, spur, gear teeth. Okay, so if you remember, I kind of did a little figure last time, but you can have, this is different mating teeth. It doesn't matter the way you do them. I'm not an artist at all, but this is the center of the teeth. Basically, I kind of mentioned that some of them can have a pressure angle. So let's say this will be phi equal to 14.5. Phi equals to 20 degrees. And this will be phi equal to 25 degrees. It doesn't matter, but this is basically 25 degrees. So let's say 14, doesn't matter, okay? It doesn't matter really. So basically, this is what it means that what is the angle basically of the tooth over here, okay? That's why I try to do it a bit different, but it doesn't matter. So maybe you might be fanatic of bicycles or motorcycles, and if you want to change your front sprocket, okay, of the motorcycle, let's say of the bicycle, do you have to pay attention of how many teeth that one is going to have compared to the one at the back? Probably you're not thinking, but yes, no? All right, because you want to have a certain relation. If they were the same diameter, it should be a relation 1-to-1, no? Okay, but since they have different diameters, in order for them to be an optimal location, the number of tooth you can have into a certain gear will depend on the angle of this phi, which is what was defined as the pressure angle. So obviously, everything should be related. So just to give you an example here, I'm just going to give you a value here. So number of pinion teeth to ensure no interference. Okay, so let's say this doesn't matter. We're not going to use it anyway. So pinion gear. So let's say you have 14 pressure angle. Then let's say you have 20% pressure angle, or you have 25% pressure angle. The minimum number of teeth will be what? So for this one will be 32, 18, and 12. So obviously, the thicker, if you want, is your teeth on the gear, the less you can put, no? All right. So basically, basically this is what I'm trying to say, is that if you do the design of a sprocket, which probably you're not going to do, because what would you generally do? You will go online and say, I need to buy sprockets, okay, to build some type of gears, let's say a car or a motorcycle. You call the builder, and probably is going to tell you, if you select this one as your pinion gear, you're going to have to get this one at the back, no? All right, you will have some design. But let's say you end up working for that company and you're the one designing those gear sprockets, you need to know those things. Okay, but this is not the case over here. All right, so now remember, this is how to transfer power. So let's think about motorcycles. Talks about motorcycles because it's easier. All right, so you have the engine, and from the engine, how is generally the power transmitted to the back wheel on a motorcycle or on a bicycle? What do you have? You have a chain, or sometimes you have, if you look at the most of the Harley have a belt, no? Okay, so you can have a V belt or I mean a belt, they call it V because it has the shape, cross-sectional shape of a V, or you can have a chain. So each one is going to have advantages and disadvantages. So for example, which one do you think can transfer better? Which one do you think can transfer more power? The rubber one or the steel one? So basically the chain or the belt? Probably the chain, and that is correct, okay? But then what is the problem of the chain, which can be, for example, an advantage of the belt, is that if your front sprocket is not perfectly aligned with the back one, if you have the chains are really strong, but they're not really good in sustaining a lateral force, no? Okay, rubber is a lot better for that, no? So if you look at it, most of the time, all those customs motorcycles, what do they have? V-belts, no? Okay, because for a chain to be good, you need to have a very good alignment, all right? So you probably need some more engineering. Okay, so over here, just very quick, I'm gonna give you an idea of what would be the different forces that you will find on a chain and a V-belt in case you need to do the design, all right? All right, so the first one we're going to do is chain sprockets. Okay, so if you have a chain, so they say this would be the pinion. I'm doing the pinion, so this will be the one connected to the engine. So let's say this is rotating this way. So what is not a problem, but what is the reality that you have in a chain? You're gonna have one side which is tight, and then generally on the lower you will have some slack. Okay, so we did see before that we know moment or torque is force times the radius. So here R is radius. I mean, I don't want to put too many things here on the figures, but so let's say it should be R sub A. Let's call this one R sub B. Let's say it would be A and B. So basically, if I do that, let's say I call this one now torque A, and this would be torque B. What will you have? You will have TA. I mean, we have to do another figure. So let me go to another page. We have this, or from here, or just say F, the force created would be equal to the torque divided by the radius. I mean, all this is basic equations. This should be page 83. page 84. So, all right, let me redo a figure here. I didn't do a very good job, but doesn't matter. This is just for the representation. So let's say we have here. This is T sub A, T sub B. So let's say here the force of the chain would be F of C, and here will be the same force of the chain S of C. So we look from this side. This should be equal to what? Should be equal to, this is A and B. So will be equal to torque A divided by R sub A, and this will be TB divided by R sub B. Okay, so this was the tight side. This side we say was slack, no? So what should be the force on that side? It is slack. It will be 0. Okay? So if we look here at the force F of C, doesn't matter which way we plot it. So let's say I do up over here this way. You will have one component that will be F of Cx F of Cy, and this will be the pressure angle, the angle here, or whatever, call it phi. They call it theta because it can be different, okay? Don't call it phi, theta. So from simple trigonometry, you have F C of x will be equal to F of C cos theta, F C of y equal F of C sine theta. Okay, and call here theta will be the angle of inclination, which sometimes is equal to the pressure angle, but that will be on the ideal case, okay, which is rarely happens. Okay, this is gear A, gear B. All right, we know the break of the force, so we have the torques, we have the moments. All right, so let's put one thing over here. This is, if there is a force here, this would be a force on the gear here, F sub A. And it would be another force here applied to this one here, F sub B. Okay, so let's say here we look at, for gear A, so this is like always, okay? Same procedure. Free body diagram, we apply Newton's equation. So in this case would be summation of forces equal to 0. will give you what? So we can say over here, let me look at the figure. Okay, so let's say you will have here, let's just look at this one over here, okay? You will have, let's say, f of c x minus f of a will be equal to 0. But this is, I call it, sorry, I call this one f of c. So let's not put f of c. So we're going that direction. No, you can put f of x. It's fine. F of x. Fc of x. So this will give you that f of a equal to fc of x. Which is equal to f c cosine theta, which will give you f of a equal to t over a over r sub a cosine theta. Okay, because we know f of c is t sub a over r sub a. All right, so similarly, for gear B, you could find what? You will find f of B will be equal to t of B, r of B cosine theta. So, what are f of A and f of B? This, what is point A? Point A, point B will be the shaft, no? Yeah, so will be the bending force acting on the shaft in that direction, correct? Okay, so you can say here, the bending force acting on the shaft is F bending equal to torque over R cosine theta. But in most cases, the angle of inclination is unknown and assumed to be very small. So if it's small, what does it mean? Cosine theta will be approximately equal to 1. So this is data that I've never seen it in a problem. Okay, so that the bending force is approximated as F, I call it bending, equal to T over R. Okay, so this is for the chain sprockets. So now we're going to do a similar analysis for V-belts. V-belt shifts. Okay, so let's say you need to design the transmission of a motorcycle. You need to decide between a chain sprocket or a V-belt. So let me redo a figure again. A, B, so same figure as before. T, A, T, B. But this time, okay, so I'm gonna have to redo another one. I don't want to put too much on each figure. So now on a V-belt, do you have a tight side or a slack side? Generally, they will be the same, no? Okay, so in this case, the only difference will be is that you will have here T sub A, T sub B, but then you will have here F of 1, F of 1, F of 2, F of 2. We'll have again the force here, FA, FB. Okay, and the only condition here will be what? That, and this is makes sense, F1 should be higher or lower than F2. If they were equal, what would be the problem? If they were equal, nothing will be moving, no? So in this case, generally the one on top should be, I mean, not generally, it's always that case, the one on top should be higher than the one at the bottom. Okay, so as before, because, I mean, you could measure what is the inclination angle, but I don't want to complicate too much the equation. So let's say neglecting inclination of the belt, of the V belt. We do summation of forces equal to 0. So let's say we look at gear A, just at this one over here, okay? Just this figure. This will give us what? Minus FA plus F1 plus F2 equal to 0. It should be a small angle, but, or maybe not that small, but, all right, let's say that we do an approximation. So this one will give you that the force F of A equal to F1 plus F2. Now we do the same thing, but for the moment equation. So summation of moments about point A equal to 0. We take these moments. This will give us what? TA. Now be careful. So TA will be positive, then this one will be negative minus F1 times R sub A plus F2 R sub A So this will give you what? F1 minus F2 R of A equal T sub A, or F1 or TA over R sub A equal to F1 minus F2. Okay. All right, so let me just rewrite these two equations. Okay, so the first equation is no problem at all. F of A equal F1 plus F2. This is our first equation. But then the second one is TA over RA equal to F1 minus F2. But what do we know? We know that FA is what is equal to TA over R sub A. So that equation here, we can write it as F sub A equal to F1 minus F2. And this will be our second equation. So basically now, just thinking about mathematics, we have two equations and three unknowns, which are F1, F2, and FA. So if there's two equations and three unknowns, can we solve that problem? No, okay? So in order to be able to solve the system FA equal F1 plus F2 and FA equal F1 minus F2. It is known, or it is, I mean, I don't know if it's known. I don't really know from where they get it, but they say that the ratio F1 over F2 is equal to 5 for V-belt sheaves. So I guess they get all this stuff experimentally, and that F1 over F2 is equal to 3 for flat belt pulleys. Okay, so basically, depending on the type of belt you choose, you can have a different ratio of F1 over F2, which then will let you solve for what would be the bending force, okay? That would be T over R, okay? And F1 and F2, the forces on the tension. Okay. All right. So let's see. Okay, so let's select the first one. So let's say, for instance, if f1 over f2 equal to 5, then I don't know, what does that mean? F1 equal to 5 f2. So I don't know, if we go and substitute into, let's say, so let's go back now to these equations here. So let's say substituting into TA over R sub A equal to F1 minus F2. This is going to give us what? TA over R sub A equal to 5 F2 minus F2, which will give you TA over R sub A equal to 4 F2, or this will give you that F of 2 equal to TA over 4 RA. All right, so almost done. So page 87. So now we know that F2 equal to TA over 4 R sub A. And we know that F1 was equal to 5 F2. Okay? So let's say from equation 1, what is what? FA equal F1 plus F2. So we're gonna have what? We're gonna have 5 TA over 4 R sub A plus F of 2 will be TA over 4 R sub A so this will give you that V sub A equal to 6 over 4 will be what? 3 over 2, no? 3 over 2 TA R sub A. So in that case, this will be the bending force. Remember, when I did the figure initially, it's always the same figure. this is point A, but point A is going through a shaft, no? So if you think about it, what we do here, figure, this is your gear A. This is your shaft. All right, this is gear A. Your point A is right here. So the bending force here would be, let's say, F of A would be creating a bending force on this shaft over here. Okay, the next section is very important, but like this one, I'm not a big fan of it. All right, so it's called stress, concentration, factors. Okay, so basically, if you do a good finite element of this, you don't need it. But if you do a design without doing any support, any finite element, the way to account for this effect is by using concentration factors. And let me talk about which effects I'm talking about. Okay, so the easiest one is what is known as the shoulder fillet. So that one, you use it many times in CATIA. So for example, if you have, let's say, a shaft over here. So this is your shaft. And let's say your shaft is connected to another shaft of different dimensions. All right, so let's say this one has a diameter, whatever, D1. But this is not important, the diameter. So D1, and this would be D2. Okay, so what's important here is to talk about this area over here. I mean, you probably know what I'm talking about when I say the fillet. This should be 2 L's. What does it mean? Is that you can have a connection. So it's this area, you could have what? Could be like the one I've done here. That is straight, an angle, or could be what? Could be, you could round it off, no? Okay, you do a fillet of different angles. And in that case, what's going to happen? So let's say this is sharp. And this is rounded. So I'm talking about this section over here. Let's say I amplify it. So what will you have? You will have a factor K of T equal to 2.5 for a sharp edge and a K of T. What should you think? Should be higher or lower? Should be lower, no? Should be less concentration of the stresses. 1.5 rounded. So basically, what is the stress concentration factor? Basically, maybe I should have said that at the beginning. So the stress concentration factor is a factor that you need to multiply the stress that you find, the normal stress that you will find on this shaft, okay? You need to multiply it by 3 because of the sharp edge. Does that make sense or not? Okay, if it's sharp, what does that mean? Is that here, the stress does not have area to be distributed. If you make it round, you have more area to distribute the stress, no? Okay. Okay, so let's put over here. I forgot to put it, so. So the K T is the concentration factor. Okay, so the concentration factor is a value by which the stresses are multiplied to account for the different geometry. Okay, so if it's sharp, it's 2.5. If it's well rounded, you will take 1.5. All right. Now, the other one that is important for shaft design is key sits. Does anyone knows what is a key sit? Obviously for shaft design, not for something else. Okay, so when you have the shaft and you have the gear, you need to mount. This is your shaft. You need to mount your gears, no? Okay, so Johnny, this is done in two different ways. So you can have your shaft over here. And what you can do is that you can mill. So you can make like a groove, no? Using a mill. And your gear will also have like a little extension where you can connect this to the shaft. Does that make sense? All right. So obviously you might have 3 or 4 around the shaft, no? Where you can connect it. It's not only one at the top. You have one at the top, one at the bottom, and one on each side. Okay. So obviously these little grooves in the shaft are going to produce stress concentration factors, and those will be different values for K. So this is what is known as a profile key. So if I do the side now diagram, that will look like something like this. One, two, three. Okay, so this is what is known as a profile key. And this one, the process to do it will be with the mill machine. So it will be mill, like the one you have here on the labs. All right, you will hold it, you put a mill machine and you will do it. The other one will be, so the other tab would be to use what is known as the sled runner. And this one, the manufacturing is a lot easier. So basically what you do, let me do the figure, I think it would be clear. So this will be from the side and from the top. it will look like. Okay, and this one generally is done with a circular cutter. Okay, so I mean, obviously it depends on the equipment you might have, but generally you will buy. This one is a lot easier to do than this one, no? Okay, this one you just take it and basically you put it. So basically you imagine you have your circular saw. This is the top, you put the top this way. So that's why it's doing this edge over here, no? The round edge, correct? Yeah. Which one do you think is better? Looks, this one's going to be much better, no? We need to have a mill machine. All right. Need to have a miller. So basically, the coefficients, the concentration factor will be K of T will be equal to 2.0 for a profile, and K of T will be equal to 1.6 for a sled runner. All right, and one last one I'm going to do over here. Retaining groove. So this one is just you take some material off all around the shaft where you're going to put your gear. And then this one, we have a KT value of 3.0. Okay, so basically I'm saying all this stuff because you make the design of a shaft, but also you're gonna have to think about how you're gonna manufacture your shaft. If you manufacture your shaft, it's gonna introduce different stresses values, okay, on how you do it.